My name is Joshua Bardwell. I'm a wireless engineer with Connect802, and I'd like to talk to you today about a very interesting phenomena that affects wireless networks called the unbalanced power effect. As we talk about the unbalanced power effect, we're going to be using this example that I've got before me. Now, this is a office floor plan that I literally just searched on the internet for office floor plan. I didn't want to use an actual floor plan of one of our customers or anything like that for obvious reasons. So if you're looking at this floor plan and you're thinking, hey, that's my building, it was just on Google Images, so don't worry. What I've done here is I've imported this floor plan into Motorola Land Planner, which is the software that we use for our 3D CAD modeling of RF coverage. And then because the floor plan came in as a PNG image as opposed to a CAD drawing, I've manually drafted the walls, and you can see what I've done if I just temporarily disable the image. I've manually drawn the walls so that the CAD software has an idea of where the walls are. Now, actually, you'll notice, for example, that I haven't drafted in the doors, and I've taken some shortcuts with laying in the walls. For an actual customer job, we would do more detail than this, but for this demonstration, I took some shortcuts. So let me just turn that image back on. That'll come back in, and we'll get started. In order to talk about the unbalanced power effect, we first need to understand what we mean when we define the range of a wireless communication. So I've placed a simulated access point into this environment, and let's just take a quick look at the specifications for that access point. So the access point is operating in the 5 gigahertz band, and it's transmitting at a power of 100 milliwatts, and this is typical for the top power, the top output power of an enterprise grade AP, like a Cisco access point or whatever. Some access points do go higher than that. Many of them don't, though. So we'll just pick this as an arbitrary starting point. And I can then ask the software to run a coverage prediction for me and show me a predicted heat map for this access point. And if I go into the configuration, I'm going to ask it to give me one contour at negative 62 dBm. And the reason I've selected negative 62 dBm is because that is a signal level that is consistent with what many enterprise-grade access points need to achieve their highest possible bit rate. So whatever the highest bit rate that the access point can achieve, that's oftentimes going to be achieved around, say, negative 58 to negative 63 dBm. So that's the number we'll use for this example. I'll go ahead and run that contour. And here's what we get. Now, if we were doing a network design and we were targeting the maximum possible bit rate, which most enterprise designs these days are doing, then this would be what we would think of as the effective coverage area of this access point. It's important to understand, just from a general perspective, that the access point's coverage does not stop at this level. This is the boundary within which client devices will achieve negative 62 dBm and therefore will be able to get the maximum bit rate possible. But the access point signal doesn't just stop at negative 62 dBm. And if we run another contour and we use two contours with 30 dB separation between them, that means we're going to get a negative 62 dBm contour and a negative 92 dBm contour. Now, negative 92 dBm is getting down to the range where the access point signal is essentially equal to or below the background noise and basically is effectively dead, okay? So if we were to define the absolute hearing range of the access point, the range within which you could hear the access point at all, this is approximately what it would be. And let's take a look at that. Aha, so much bigger. So one thing to keep in mind when you think about an access point's range is that if you're targeting a maximum bit rate, you might be thinking about the negative 62 dBm contour, but from a wider perspective, for example, from the perspective of co-channel interference, there's a lot more signal going out into the environment that may or may not be considered usable by you. Would a client here be able to associate with this access point and transmit data? Yes, absolutely, but it wouldn't be achieving the data rates that you were targeting for the design. Now, none of that is directly related to the unbalanced power effect, which is what we're talking about here, but it is an important perspective that I thought was significant enough to call out just sort of in passing. All right, now let's place another transmitter in the environment. And we're going to place this transmitter near the edge of the AP's coverage area. So let's put it right about here. Maybe it's at the reception desk. And it's technically inside the coverage area, so it should be able to achieve the maximum possible bit rate. We'll just rename that device real quick. But we're going to make this device transmit at only 25 milliwatts. And we know that there are many devices out there, laptops, whatever, that can transmit at 100 milliwatts. But many devices, especially mobile devices, don't transmit at the maximum possible output power that an access point would because they're trying to save battery. So we'll give this device a 25 milliwatt transmit power compared to our access point's 100 milliwatt transmit power. And if we run a coverage prediction for this device, we're going to do that at negative 62 dBm, just like before, one contour. Let's look at what happens. So what do we see here? The client device is within the negative 62 dBm boundary for the access point, but the access point is not within the negative 62 dBm boundary for the client device. And what that means is that the access point will be able to achieve maximum bit rate communication downstream to the client device, but the client device will not be able to achieve maximum bit rate communication upstream to the access point. And the reason for that is that the client device is transmitting at a lower transmit power than the access point. By way of example, you can imagine if we were standing on opposite sides of a big canyon and you had a megaphone and I didn't. You could talk to me, but I couldn't talk to you, right? You wouldn't hear me when I talk back because I'm not talking as loud as you are. In 802.11, we see the same thing, and that's the unbalanced power effect. Now, one simple effect of the unbalanced power effect is that if you insist that all devices be able to achieve maximum bit rate, both upstream and downstream, then you have to design the network based on the transmit power of the weakest client device. So if our client devices are at 25 milliwatts and our APs are at 100 milliwatts, then if we design based on the 100 milliwatt output power, we will get full data rate downstream, but we will not consistently get full data rate upstream. If we design based on a transmit power of 25 milliwatts, though, then we're using the lowest common denominator, and we will get full bit rate both upstream and downstream. Now, the unbalanced power effect does not mean that client devices will never achieve the maximum bit rate. This client device is at the very edge of the AP's coverage area, but I think we can see that if we move the client device closer to the AP and rerun that prediction, now the AP is just on the edge of the client device's negative 62 dBm contour, and the client device might be able to achieve, any client device in this location might be able to achieve the maximum bit rate possible, both upstream and downstream. And if we move it even closer, we can see that there are many areas within which the client device would be able to achieve the maximum bit rate possible. And in fact, we can run a 25 milliwatt contour for this AP, and that will show us what that area is. So now if I set the AP to 25 milliwatts and rerun the contour for the AP, this is the area within which a client device at 25 milliwatts will be able to achieve the maximum bit rate. And if we then set the AP back to 100 milliwatts, and rerun the prediction again, this is the area within which a client device at 100 milliwatts will be able to achieve the maximum bit rate. Now, I did something there that may not be entirely obvious. You might be wondering, why did I change the AP's transmit power and then use the AP's 25 milliwatt coverage contour as a representation of the area within which a client device at 25 milliwatts would be able to achieve negative 62 dBm upstream? In other words, why did changing the downstream transmit power tell me something about the upstream signal strength that a client could achieve? And the answer to that question is something called reciprocity, which basically says that downstream and upstream on a wireless link are just, they're exactly the same. There's no fundamental difference between them. So if we assume the same transmit power, the same antenna gain and everything, then there's no difference between the upstream and the downstream direction. So if I do a downstream prediction at 25 milliwatts from the AP, that's the same as saying, show me the area within which a client at 25 milliwatts would achieve negative 62 dBm upstream to the location of this AP. There's one more thing to keep in mind here, and that is that just like the AP's coverage did not just stop at negative 62 dBm, but continued out at lower and lower signal strength through the rest of the building, the client device's coverage does not just stop at negative 62 dBm. So here we've got the client device within the AP's negative 62 contour, so we will achieve maximum bitrate downstream. But if we run that contour again for the client device, we see that the AP is not within the client's negative 62 dBm contour, so we will not achieve negative 62 dBm or maximum bitrate upstream. But if we rerun that contour, and instead of just one contour, we do 3, and we set 10 dB spacing between them, so that means our contours will be negative 62, 72, and 82 dBm. We'll rerun that contour, and what we'll see is that although the AP is not within the client's negative 62 dBm contour, that's the yellow one, it is within the client's negative 72 dBm contour, that's the green one. So client signal strength upstream will be based on a signal strength between negative 62 and negative 72 dBm. And that may still be a perfectly fine data rate depending on the type of traffic you're carrying. In many scenarios, the majority of traffic is going to be downstream and very little traffic is actually going to be upstream. If that's the case in this environment, we could hypothetically design this based on the AP's 100 milliwatt transmit power, and we would accept that we would get the full maximum bit rate downstream, and we would not get the maximum bit rate upstream in 100% of the area, although we would get it in some percentage of the area, AP or client devices that are closer to the AP. And that may be an acceptable trade-off to help reduce AP density and save you a little bit of money while not really reducing client performance in any meaningful way. So what's the takeaway from this? The unbalanced power effect occurs whenever an access point is operating at a higher transmit power than a client device. And what the unbalanced power effect means is that if you want to have equal throughput in both the upstream and the downstream direction, you need to design your network based around the minimum transmit power that a client device will have. Alternatively, you can accept that there may be less upstream than downstream throughput and design based on some higher transmit power than client devices will have, if that's an acceptable trade-off for you. Thanks for watching. See you next time. I hope this video has been helpful to you. Whatever your wireless needs, from indoor office Wi-Fi to outdoor 60 gigahertz point-to-point microwave, 400 megahertz spectrum analysis services, wireless network design, survey of existing buildings, troubleshooting of wireless networks that are not working up to spec. Whatever it is you need related to wireless, Connect Data 2 is your resource for commercial wireless data networking. With 20 years in the wireless networking business and over 1 billion square feet of area design, chances are that whatever your wireless needs, not only can we do it, but we have done it. Please give us a call or an email today.